Assalamu alaikum. Welcome to lecture 6 of NLP. So today we will continue with our discussion on text representation. We had introduced the representation which is known as the tf-idf. We will start with that today and then move on to the application of information retrieval. And uh, basically, information retrieval is a traditional application of NLP, which has been around for quite a while and is quite a successful application. And we will start with that. And in particular, we'll focus more on the evaluation of IR systems. And this is something that we will be seeing multiple times in this course. Evaluation is very important in NLP. For many of the models that we will be using in practice, you will probably be using off-the-shelf models, but evaluation is something that you will be doing on your own as a NLP expert. So evaluation is something that we will be emphasizing in this course. So we'll talk about IR evaluation and then we'll move on to some basics of text classification, logistic regression, and neural networks using the same representation. So I think that would be all for today. Probably we won't be able to start logistic regression. So that's the agenda for today. Any questions? Any questions? All right. So in the last lecture, we talked about minimum added distance, which is the string distance between two strings. I think one other thing that I would like to add, because which is also commonly used in practice, is what is known as the longest common LCS. So this is a measure of similarity between two strings, and it is based on the minimum added distance. Uh, the idea in longest common subsequence is you align two sequences X and Y, and for that alignment you will have to do dynamic programming. You will have to run through the minimum added distance algorithm. Once you have the alignment, you simply count the sequences, the subsequences, the number of subsequences that are common in the two strings. So that would become the longest common subsequence. So, all right. So as I said, this is a similarity. And I'll just take an example. Let's say we have two strings, let's say PLAGUE, plague, and BLUE, blue. Okay. So if you do a minimum added distance, and by the way, for minimum added distance, you will have to choose some cost for insertion, deletion, substitutions. That would depend on the application. For typically for computing LCS, we will use cost of 1 for insertion, 1 for deletion, and 2 for substitution, meaning that substitution consists of insertion and a deletion. But of course, you can use any other cost as well if that is defined or appropriate for your application. So if you align this, so we have plague and we have blue. So basically P, L, A, G, U, and E. And then we have B, L, then star, star, and then U and E. So the two the two strings are now aligned. So you have two characters that match U and E, and there is also another character that match that is L. We actually count all characters in LCS. So the longest common subsequence for this is LCS for X and Y. In this particular case would be 3. Okay? So this is a similarity, and for computing the similarity, you need to do a minimum edit distance because you need an alignment. Without an alignment, so so that's right. So minimum edit distance requires basically the minimum number of edit operations required to move from one string to the other. But in the process, you're also doing an alignment. And for longest common subsequence, you basically count the sequences that match in the two strings. So in this particular case, there are 3 characters that match in order from the first string and the second string. You can also have a normalized LCS, which may basically simply LCS divided by minimum of length of X and length of Y. ठीक है? So in this particular case, LCS 3 था, minimum length is maybe for blue, which is 4. तो ये आपके पास एक normalized similarity आ जाएगी between 0 and 1. So, uh, so this has almost the same applications as minimum edit distance, but this is somewhat more commonly used, especially if you are comparing system extraction or generation output with gold standard. ठीक है? So let's say आपके कोई समराइजेशन या ट्रांसलेशन की प्रॉब्लम थी, आपके सिस्टम ने कुछ सेंटेंस जनरेट किया और आपके पास एक गोल्ड ट्रुथ का सेंटेंस भी है. To see whether these two sentences match, you can use longest common subsequence. You do an alignment and then you count the number of characters that are the same in sequence in the two strings. And if you want to normalize it, you divide it by the length of the smaller string. Okay? So this was from the last topic. And of course, this is not in the book, but as I said, this is used commonly in practice. So I mentioned this in the course. Book में नहीं ये दिया हुआ. All right, any questions? So next, we had talked about text representation. We said that we had a document which is our larger unit of interest. Document, ठीक है? D. So this could be anything of interest. If it is information retrieval, this is the document or the unit. LCS, yes, it's for consecutive characters. Basically, it's sequence है, ठीक है? So you align and then you count the number of characters that match in the two strings. Obviously, if there are multiple characters that are consecutive, then obviously we'll be counting those as well. But let's say आपके पास मतलब सिर्फ let's say L इधर मैच हो रहा है और उधर U मैच हो रहा है. Only one, तो obviously LCS would be 2. ठीक है? जरूरी नहीं हो consecutive हो. They could be very far apart, but they are matching. ठीक है? All right. Okay, the document D could be anything, an email, a tweet, it could be an article, a web page, and so on. ठीक है? So this is our unit of interest, the larger unit of interest. Usually the smaller unit of interest is the word, which we typically call the term. So in other words, this is sometimes call it a term, we call it a word, we call it a, let's say, subword also, or token in general, and so on. Okay? So we will use multiple names for this. All right. And typically what happens is you usually have a collection of documents. So D is a collection of, so D, small d, would be in a capital D, where capital D is a collection of documents. And we can say is basically N. And of course, T is a term usually comes from your vocabulary. So this is the vocabulary that we have already talked about. It could be made of words or subwords or tokens in general. So, and this size, let's say, is M. So you can then represent each document with, so each of these terms is a feature, and this feature captures a characteristics of each document in the document collection. So we can represent each document, each doc, as a vector of size M. Okay? And if you collect all the representations in the collection, we have what is known as a term doc matrix. ठीक है? So term doc matrix का size क्या होगा? How many terms do we have? Those would be the number of rows by n. So of course the shape of this matrix can be in different forms. Sometimes ये doc term matrix में ज़्यादा convenient लगता है हमको. So in this case, this n by m matrix. ठीक है? So each row is now a vector for a given document. ठीक है? All right. So अच्छा, क्वेश्चन वापस एलसीएस का भी आ रहा है. तो एलसीएस, so LCS is a similarity, and so can you mention the question again? Maybe you can speak up because I didn't quite understand it. Minimum added distance के साथ आप compare करना चाह रही हैं? अच्छा, ठीक है. So uh, actually minimum added distance includes insertions and deletions as well. ठीक है? Uh, in this particular case LCS में हम सिर्फ substitutions count कर रहे हैं, और वो substitutions जिनमें there is a character change. When there is no change, we actually don't count. Actually, that would also not be present in MED. So हम वही count कर रहे हैं. हम insertion deletions, if there are any in addition to substitutions, वो count नहीं हो रहा longest common subsequence में. ठीक है? It's not a exact opposite of minimum added distance. LCS not an exact opposite of minimum added distance. ठीक है? But as I said, to find LCS, you have to do an alignment. And alignment के लिए वही process चलेगा dynamic programming वाला. Okay. So, okay, last time, so we talked about the tf-idf representation for a term TM. So for each, so matlab, let's say if you have a document D1, you will have values for each word in the vocabulary. So let's say we talked about this last time as well. Features, let's say आपके पास let's say D है, A है, let's say excellent है. So for document D1, you will have a value V1 for D, V2 for A, and V3 for excellent, and so on. So ये value क्या है? This value is given by tf-idf for a term T, which maybe let's say D, the word D, and for a document D, in this case D1. And we said that this is multiplication of two things, tf of D multiplied by idf of T. Okay, the term T. So let's write these formulas again. So what is tf of T and D? So this is basically log 10 of count of T, D plus 1. Okay, this is for the case when count T, D is greater than 0 and it is 0 otherwise. Okay, so this is TF. So in other words, this is directly related to the number of times a word occurs in that particular document. It's directly related. Simply we are taking a log of it so that it squashes it out. Okay, and in a way, log is a way of normalizing it or squashing it. There can be other ways of normalization as well. ठीक है, ये हो गया हमारे पास. So this depends on only that document. So what is IDF? So IDF is defined for a term T in the whole collection. And this is basically log 10 of n, which is the total number of documents, divided by document frequency of term T. So the expression in the parenthesis n over dfn is the inverse document frequency. So in other words, df kya hai? This is the number of documents that contain term T in the collection. And ऊपर आपके पास n है. So in other words, df over n is the document frequency. ठीक है, उसका normalized form में we are taking the inverse n ऊपर कर दिया, हमने df नीचे कर दिया. ठीक है. So this is IDF, and as I said before, tf-idf is the multiplication of both of these terms. So this is the most popular way of weighing each word in a term document or document term matrix. Given a collection of documents D that are defined over a vocabulary set V. So let's see. TF का तो हमने कहा था कि it increases with the number of words in the document, and it depends on the term in that document only. While IDF depends on the terms that appear in the entire collection. Okay. So what happens? Let's say आपके पास so IDF of, let's say मैं word D कहता हूँ, just as an example. So log 10, ठीक है. Let's say आपके पास 100 documents हैं. So the word D usually would occur in almost every document, right? It's a popular word English में. What do you get? So IDF is 0. So if a word occurs in all the documents in the corpus, then its IDF would become 0. And if its IDF becomes 0, then obviously TF IDF would also become 0 because IDF multiplies with TF. Okay? So this is kind of reducing the importance of words that occur frequently in the corpus. So this is the primary purpose of IDF. So if a word occurs less frequently in the corpus, then that word would have a higher weightage. So let's say मैं IDF of excellent निकालता हूँ. So log 10, again, this is a hypothetical example. Let's say it only occurs in two documents. So 1.69. Okay? So this is going to be a large number, and then you multiply this with TF of a particular term of the particular document. Okay? So there's a slide. So these are some IDFs calculated from Shakespeare's writing. So Shakespeare, I think, has 37 different books or writings, different writings. और उसमें ये words की IDFs लिखी हुई हैं. So the word Romeo occurs in just one writing or one book, and so its IDF is obviously large. So forest, for example, occurs in 12, so it has a much smaller IDF. Battle occurs in 27, it's even smaller. So the word good, for example, occurs in all the writings, so it has a IDF of 0. So can someone again now tell me why we would like to have IDF in our weighing scheme? तो इसका क्या पर्पस होगा? थोड़ा सा मैंने बताया तो था, but someone again would like to reiterate the usage of IDF. IDF क्यों helpful है? कोई एप्लीकेशन जिसमें IDF का usage would become very critical, for example. ठीक है, so that's a valid comment. So exactly, so if a word occurs in all the documents, so obviously that word is not a distinguishing feature. And usually when we are analyzing multiple documents from a collection, we are kind of usually interested in finding or distinguishing one document from another document. So this is the case in the application of information retrieval, which we are going to discuss today, as well as it is in the case of application of text classification as well as clustering. Although clustering explicitly हम discuss नहीं करेंगे, but if you want to do clustering of documents, then words like D, A, which would occur in all the documents, would not help in your clustering or not help in your classification and not help in your information retrieval. That's an important point. Is there anything else? So another important factor that IDF brings is it kind of pushes these words and their values to 0. Okay? So forces values of words or other tokens or other features that appear frequently to 0. Okay? So these features then would not play an important role in the analysis. So implicitly, so we are kind of removing those features or words in our analysis. Okay? So it's an automatic way of kind of reducing the impact of words that occur that are not relevant and kind of removing them from our analysis. फॉर दोज हु हैव टेकन मशीन लर्निंग, इसको का पैरेलल नजर आता है आपको? मशीन लर्निंग में इस तरह के कंसेप्ट, बड़ा इंपॉर्टेंट कंसेप्ट मशीन लर्निंग में यूज होता है। यहाँ तो एक्सप्लिसिट नहीं है, वहाँ एक्सप्लिसिट होता है। एनीवन रिमेम्बर? 331 तो सारों ने पढ़ा होगा, एंड ऑल्सो पीपल हैव टेकन 535 आई गेस। Right. So I got the right answer, regularization. So you might have studied regularization in your machine learning. So machine regularization is a way of forcing features that are not relevant to zero. So in this way, IDF serves like a regularizer for many of our NLP problems, especially when you are using the tf-idf representation. Okay. So obviously this is not a machine learning course, so I won't be able to go into details of regularization and other stuff. But for those who have taken this, and they must have taken this, so they can go back and refresh their understanding. All right. So implicitly हमारा feature set हम छोटा कर सकते हैं। Vocabulary usually बहुत बड़ी होती है, इस तरह हम vocabulary को छोटा भी कर सकते हैं। ठीक है? All right. So we know how TF-IDF is computed. ठीक है? सो यूजली अब हमें आ जाता है एप्लीकेशन इंफॉर्मेशन रिट्रीवल पे। सो दिस इज ए पॉपुलर एप्लीकेशन in NLP as well as in text mining. The idea here is that we are given a collection of documents, which, as I said, could be emails, corpus, emails, tweets, and whatever, web pages, articles. And as a user, we would like to retrieve relevant information that we pose as a query. ठीक है? So query based doc, ठीक है? So we pose our question as a query, and in the simplest form, the query is a set of keywords. So query key Q is a set of key words or simply words. So these are words of interest, and we would like to find the document that contain these words uh, in the collection B. So in the simplest form, the query Q is also represented is also represented as a vector of size m. m क्या था? Vocabulary size, right? So let's say मैं एक query लिखता हूँ जिसमें सिर्फ let's say just take an example. Let's say m, let's say is usually vocabulary size is typically large as we had discussed. Let's say आपने word use किए हुए हैं, formal language है तो usually around 20,000 होगी, 20,000 है। तो आपने कोई query लिखी, उसमें let's say आपने लिख दिया whatever, I mean, I'm just trying to find a good example. Uh, so for example, capital, and let's say you write France. ठीक है? Just two words. So this query has just two words, and vocabulary size is obviously quite large. So you will be representing this Q also in a vector of size 20,000. Most of them would be zero. ठीक है? जहां आपके पास आएगा कैपिटल वो वन हो जाएगा, और जहां आपके पास आएगा फ्रांस वो वन हो जाएगा, बाकी सारे जीरो होंगे। सो दिस इज ए स्पार्स वेक्टर। ठीक है? एंड रिमेंबर आवर D was also a vector of the same size, एंड दैट इज ऑल्सो यूजली स्पार्स. एक डॉक्यूमेंट में पूरे 20,000 डिस्टिंक्ट वर्ड्स तो नहीं होंगे, राइट? But of course, usually a query would be much, much smaller than a document. So you can say that its sparsity is much higher. So हमारे पास अब ये दो documents हैं represented in the same sparse vectors has a large number of zeros. Uh, One hot encoding something different है, वो हम discuss करेंगे आगे जाके. But one hot encoding में just one word usually होता है, one, and बाकी सारे zeros होते हैं in the vocabulary sized vector. In this case, usually one नहीं होंगे, multiple words होंगे, but still the number of words that are non-zero are very few as compared to the total number of words uh, in the vector which would be zero. ठीक है? Okay, so how do you know the similarity between these two vectors? So we have a query and we want to find the best match for it. The most common technique and still very popular is cosine similarity. ठीक है? So the cosine between Q and D क्या होगा? आपने कई जगह पहले पढ़ा होगा. It's basically Q is a vector and D is also a vector of the same size. Basically, we take the inner product and of course denominator में और denominator में the lengths of the two vectors. In other words, cosine similarity is the normalized inner product. Numerator में inner product है and denominator में simply division by scalars, two scalars, the length of Q and the length of D. By the way, ये lengths L2 norms हैं, ठीक है? Square each term, sum it up and take the square root. ठीक है? So, so can someone tell me कि cosine similarity का range क्या होगा in general? What would be the range for the values of cosine similarity? Mhm. Okay, good. Uh, so we have two suggestions, -1 to 1, ठीक है? And also 0 to 1. So जो 0 to 1 कह रहे हैं, okay, जो 0 to 1, okay, that's fine. All right, ठीक है. So -1 to 1, that's theoretically that's correct. The cosine similarity between any two vectors, uh, Q and D, is ranges from -1 to 1. But in most of NLP, at least for the vectors that we have developed, you notice that the vectors that we have developed do not have negative values. Do they have any negative values? So they don't have any negative value. So TF जो है, it is non-negative. IDF is also non-negative. So tf-idf is always going to be non-negative. इसका मतलब है कि जब भी आप Q और D की आप cosine similarity लेंगे, the inner product numerator में would always be positive or zero. ठीक है? So in this particular case, the range would be 0 to 1. ठीक है? And 0 means that the two vectors are orthogonal if you represent those vectors in space, and 1 means that they are collinear. ठीक है? So they are similar. So actually इसको आप विजुलाइज कर सकते हैं. आई डोंट हैव द डायग्राम विद मी. सो बेसिकली आप जब what is happening is you have a vector for q, you have a vector for d. First you normalize it them to unit vector. So ये लट से छोटा था वो बड़ा था, दोनों यूनिट वेक्टर हो जाएं. q इतना है, d भी उतना है. सो इन अदर वर्ड यू गेट ए स्फीयर. उन स्फीयर्स पे ये दो पॉइंट लाई करेंगे. स्फीयर का जो डायमीटर रेडियस होगा वो 1 होगा. ठीक है. सो इफ दोज टू पॉइंट्स are on this at are collinear, meaning that they are at the same point, their similarity would be 1. If they're 90 degree apart, एक इधर है और दूसरे उधर है, for 2D, so uh, their similarity would be 0. ठीक है. So the cosine similarity is used to quantify the similarity between a Q query and a document D. ठीक है. uh, but just to emphasize, this is not the only way. So in other words, we are scoring. We want to score a query with a document D. So we say that this is cosine of T and D. Okay? This is one way of saying that you can score it directly as a cosine. But in practice, usually more sophisticated techniques हम इसके साथ augment करते हैं. So we will not mention those in detail, but let me mention a few things here. T plus D. So A times cosine of T and D plus B times some other measure, uh, let's say alpha, some other function of T and D plus C times beta of T plus D and so on. So इस तरह का फंक्शन होगा स्कोरिंग का, where A plus B plus C is equal to 1. तो आपने कुछ वेटेज कोसाइन सिमिलैरिटी को देना है, कुछ वेटेज किसी और सिमिलैरिटी फंक्शन को देना है विच आई एम कॉलिंग अल्फा, एंड उसका वेट बी है. और कुछ आपने वेटेज एक और को देना है, एंड देयर कुड बी मोर एज वेल, विच आई एम कॉलिंग बीटा, और उसका वेट सी है. ऑन ऑल दिस वेट शुड सम टू 1 सो दैट दिस फाइनल स्कोर रेंजेस बिटवीन 0 एंड 1. ठीक है. ई इज द टर्म. सॉरी, टी नहीं चाहिए, क्यू चाहिए. सॉरी, सो दैट्स राइट. सो ये टी नहीं था, ये क्वेरी थी. टी तो टर्म है जो पीछे हमने डिस्कस किया था. ठीक है. जो कोसाइन हमने निकाला था बिटवीन ए क्वेरी क्यू एंड ए डॉक्यूमेंट डी, वो फॉर्मूला हमने ऊपर लिखा है. बट दे कुड बी अदर फंक्शंस फॉर क्वांटिफाइंग द सिमिलैरिटी विच आई एम जेनेरिकली सेइंग एज अल्फा एंड बीटा. वो आप एक इकट्ठा करके एक फंक्शन बना सकते हैं विच इज कॉल्ड द स्कोर फंक्शन. उसमें कुछ वेइंग फैक्टर्स होंगे ए बी सी एंड सो ऑन. All those weighing factors should sum to 1 so that you get a score that ranges between 0 and 1. So score would basically then be so by the way backslash in मैं लिखता हूँ. This is the वो क्या कहते हैं, set inclusion operator. So backslash in ये latex का uh, इसका है symbol for those who are familiar with latex. ठीक है. So score would lie within the interval 0 and 1 if we take a plus b plus c is equal to 1. ठीक है. सो कैन एनीवन जनरली मेंशन के और क्या चीज हम कंसिडर कर सकते हैं इंफॉर्मेशन रिट्रीवल इन एडिशन टू कोसाइन टू रैंक ए डॉक्यूमेंट और टू स्कोर ए डॉक्यूमेंट गिवन ए क्वेरी. जी, न्यूमरेटर डॉट प्रोडक्ट ही है जी. So numerator of cosine similar to dot product, denominator में simply हम normalize कर रहे हैं. So my question was कि alpha beta और क्या हो सकता है? Maybe someone can come up with another way of quantifying the relatedness of a query with a document. So actually, depending on the application, there could be numerous ways of doing this. And as I said, this is a whole wide area which we are not able to cover in detail. So एक तो of course आपने पढ़ा होगा page rank. Anyone remember page rank? So page rank is basically a score that is given to a page based on how other pages, other documents uh, give importance to it. ठीक है? तो ये this is very important in web retrieval, web information retrieval. And this was, as you know, developed by Google in way back in 1997, I think, the page rank algorithm. So you can include the page rank score as part of that scoring function. Okay. Other things could be, for example, checking whether the query term appears in specific locations, let's say, so e.g., let's say heading, anchor text, etc. ठीक है. So let's say आपका query term में France, let's say था. So is France the heading of the document that we are trying to retrieve? So if it is the heading, then it has a greater importance. The score आप ज़्यादा देंगे. So that might be another function that you can use. And there could be numerous such other functions as well. ठीक है. All right. Uh, just a bit of history. Anyone remember Alta Vista? Alta Vista, I think, became extinct even before any of you was born, I guess. किसी को पता अल्टा विस्टा का? So no one remember. You can Google this later on. So this was one of the first uh, popular web search engine. So even before when Google came in, everyone did use Alta Vista. So Alta Vista was primarily text-based. It did not use PageRank. So, but it was still very popular, and I remember I used it quite a bit in the mid 1990s. इसी से ही हमको information मिलती थी. Yahoo was also good, but Yahoo's specialization was in curating documents themselves. It was not an ad hoc search engine. तो वो पहले ही लिस्टें बना के रखी होती थी उन्होंने, तो वो आपको दे देते थे गिवन ए स्पेसिफिक क्वेरी. तो उसमें ह्यूमन इंटरवेंशन भी थी. अल्टा विस्टा वाज प्योरली इंफॉर्मेशन रिट्रीवल बेस्ड, कि आपने एक क्वेरी लिखी है और उस क्वेरी के बेसिस पे इसी तरह का कोई एल्गोरिथम चलता है और उसके बेस you return the relevant documents. So Alta Vista was kind of the king in 1995, 96, 97, even 98 and 99 जब Google ने अपना पेज रैंक बेस्ड सर्च इंजन पॉपुलर किया, मे बी अराउंड 2000, तो फिर जाके ये खत्म हुआ. So maybe you can read up the history of Alta Vista after class. I think it should be an interesting read. All right. Okay, so there is a small topic on inverted index. वो मैं skip कर दूँ, वो आपकी अपनी reading है. Slides पे भी है, book में भी है. So by the way, this is chapter 11. of your book. ठीक है? Chapter 11 of your book, and we are going to only focus on 11.1 and 11.2 right now. 11.3 is on rag, वो हम मेरे ख्याल से 2 भी नहीं है, 11.1 ही है. 11.2 is rag, which will come back later on. All right. So now let's move on to evaluation. Evaluation, ठीक है? So how do you evaluate your IR system? By the way, information retrieval is not just for large uh, applications like library retrieval system or the web retrieval system. There are many small applications based on your computer, based on whatever application that you make, जहाँ आपके पास IR करनी पड़ती है, जहाँ आपने कुछ डॉक्यूमेंट सेव किए हुए खुद ही, एप्लीकेशन खुद ही सेव किए हुए, and then you want to retrieve it. So it could be just like emails आपने archive की हुई हैं, maybe आपने अपने notes archive किए हुए हैं, depending on the application. Medical notes हैं, कुछ और हैं, personal notes हैं, तो you probably would have to run an IR system locally. ठीक है? And typically वो जो local systems होते हैं इसी तरह ही develop होता है. There isn't any much sophistication involved there. Simple tf-idf and some scoring function से आप उसको build कर लेते हैं, you get decent results. All right. So so how do you evaluate? So we have a query, ठीक है? And this query is sent to a document collection D. D is the document collection. So what happens is for each query, we have, so for each query, you have a set of retrieved documents. So retrieved को मैं RD कह देता हूँ. So this is set of docs. And then there's also a set of relevant documents. RT कह देता हूँ. Set of, ठीक है? So एक query का there is a set of relevant documents, and your algorithm would output RT, which is a set, usually a ranked set of documents. And essentially we'll then have to compare RT with RD. Relevant and RD is retrieved. ठीक है? And based on this comparison, we will have to develop various metrics. So ये कुछ metrics हम अब discuss करेंगे. So there are a number of metrics. ठीक है? The set of relevant, depending on your corpus, benchmark corpus, usually वो human curated ही होता है. ठीक है? So humans would be able to find the most relevant document, वो set बनाया हुआ आपने. तो यूजली आपके पास इंफॉर्मेशन रिट्रीवल के बेंचमार्क्स, वेरियस बेंचमार्क डेटा सेट्स मिल जाते हैं. बट इफ यू वांट टू मेक योर ओन, देन यूजुअली आरटी आपने हर क्वेरी के लिए यूजर ही एनोटेट करेगा, यूजर ही आइडेंटिफाई करेगा. सो ह्यूमन एनोटेशन इज अनदर बिग evaluation part in NLP. So human, आजकल NLP की आप कोई भी रिसर्च करनी है ह्यूमन इवेल्युएशन के बगैर नहीं कर सकते आप. तो ह्यूमन इवेल्युएशन इज वेरी इंपॉर्टेंट. ठीक है. So let's talk about some techniques, measures in a way for quantifying the performance of IR systems. One is precision and recall, which we have studied elsewhere as well. So I'll quickly mention these. So what is the precision of a query queue? So precision is basically the number of relevant documents that are retrieved in the total number of documents retrieved by the system. So if I want to write this in terms of uh, notations, so I have RT here, cap कर लें, cap is intersection operator, RD. So what is this now? RD intersection RT. So this is the set of documents that are relevant in the retrieved, and उसके बाद बार्स मैंने कर दूं, उसका नंबर आ गया, absolute or count. So divided by RD. ठीक है? So let me write the other one, that I'll give you an example. Recall Q is the same thing. ऊपर वही चीज है, RT cap RD. अब डिनोमिनेटर में आपके पास क्या होगा? सो डिनोमिनेटर में RT होगा। टोटल रेलेवेंट डॉक्यूमेंट्स में कितने आपने रिट्रीव किए, वाइल प्रिसीजन में टोटल रिट्रीव में कितने रिट्रीव किए। ठीक है? बैकस्लैश कैप जो है लेटेक्स में इंटरसेक्शन, द इंटरसेक्शन ऑपरेटर. सो यू कैन ऑल्सो कॉल इट द बैकस्लैश इंटरसेक्ट. लेटेक में ये दोनों यूज कर सकते हैं आप. No, relevant documents are basically another total. Those are the from basically the relevant RD जो है हमारे पास, RT. This is basically also a subset in general and could be equal to D. ठीक है? By the way, this is relevant for a particular query Q. ठीक है ना? हर query का set of relevant document different होंगे. ठीक है? So that's why ऊपर मैंने Q पहले लिखा था, फिर RT और RD लिखा था. So those were the relevant documents for a particular query and the retrieved documents for a particular query. And they usually would be a subset of the whole collection in the corpus. So you can think of आपके पास एक. So can someone answer this question? How do you decide the relevant documents? उनको किस तरह पता चलता है कि एक डॉक्यूमेंट रेलेवेंट है कि नहीं है? जी, सिमिलैरिटी स्कोर. सो वी मेंशन स्कोर. ऑलराइट. सो एक्चुअली वी आर टॉकिंग अबाउट IR सिस्टम. सो IR सिस्टम में जो स्कोर मैंने पहले लिखा था, दैट इज यूज्ड टू find a relevant document, but then since score is a continuous number, so usually we'll threshold this. So score greater than equal to some theta. So this will give us our RD. So theta is a parameter that the user will specify. So let's say all documents that have a score greater than 0.8 would be in RD, and RT of course is from your corpus, your training data set, usually identified by humans. ठीक है? So any questions? ठीक है, ऑलराइट। Okay, so we have talked about precision and recall for a particular query, one query. So usually there is a trend. So you can plot the precision and recall for a given query. On the x-axis we have recall, on the y-axis we have precision. So how would you vary the precision and recall? So basically you take, remember the retrieved documents are ranked. तो आप उनको मल्टीपल चंक्स में ले लें, पहले 5 ले लें, फिर नेक्स्ट 5 ले लें, फिर नेक्स्ट 5 ले लें. सो हर एक का प्रिसीजन निकालें, हर एक का रिकॉल निकालें, एंड यू कैन प्लॉट दिस कर्व. सो दिस इज द जनरल ट्रेंड फॉर अ कर्व. तो जैसे आप आपका प्रिसीजन इंक्रीज होगा, सो एज योर प्रिसीजन टेंड्स टू इंक्रीज, योर रिकॉल टेंड्स टू डिक्रीज. ठीक है, सो प्रिसीजन हाई होगा, रिकॉल कम होगा. जब आपके पास रिकॉल हाई होगा तो प्रिसीजन कम होगा. सो दिस इज ट्रू फॉर ऑल सिस्टम्स. So you will never have a system that has a horizontal line. So it will be a downward decreasing line. ठीक है, अब इसमें से कौन सा पॉइंट हमारे लिए बेहतर है? So this would be decided by your application. So usually we would like high precision with decent recall, good recall. Or inverse be same, a high recall at decent precision. Of course, you can combine both of these to form an F score as well. But let's look at some other measures before we look at. So this was for just one query, but usually जब हम एक systems evaluate कर रहे होते हैं, we will have multiple queries. So Q है. So multiple queries आपके पास होती हैं. ठीक है. So we like to average the performance over multiple queries. So usually for precision recall, what would happen? So हमने precision भी प्लॉट करनी है, हमने रिकॉल भी प्लॉट करनी है हर वैल्यूज की. सो यूजली हमारे पास रिकॉल आप प्लॉट करेंगे, लेट्स से 0.1, लेट्स से 0.2 टू लेट्स से 1.0. ठीक है. So how would you ensure that you get a recall of this? Just increase the retrieved set size until you have all the relevant documents in the retrieved set. You will get a recall of 1. उसमें से आपने लेट्स से 50% आपने साइज को छोटा कर दिया तो 50% आपके पास आ जाएगा. सो बेस्ड ऑन दैट यू कैन ऑल्सो फाइंड द प्रिसीजन. हर एक के साथ आपका एक प्रिसीजन कैलकुलेट करेंगे आप. तो यू कैलकुलेट द प्रिसीजन एट पर्टिकुलर रिकॉल. So precision recall of 0, precision recall of 0.1, precision recall of 0.2, and so on. So this would be for, let's say, one query. But if you have multiple queries, फिर आप क्या करेंगे? हर क्वेरी का जो रिकॉल तो आप probably निकाल लेंगे, but precisions उनकी डिफरेंट होंगी. सो यू विल हैव टू टेक द एवरेज ऑफ दोज प्रिसीजंस and then you plot it. So I hope, let me give an example. ये थोड़ा सा concept bit different है. Let me give an example. Okay, so let's say अब मेरे पास एक query थी, let's say Q1. ठीक है. So Q1 है, तो इसमें लेट्स से मेरे पास रेलेवेंट डॉक्यूमेंट्स इसके 100 हैं, लेट्स से 10 है, लेट्स से 20 कर देते हैं, इसके 20 है। ठीक है, तो मेरे पास Q2 है, इसके रेलेवेंट लेट्स से 50 कर लेते हैं। ठीक है, दो क्वेरीज हैं। अब आपके पास आईआर सिस्टम होगा, वो रैंक करेगा डॉक्यूमेंट, ऑफ कोर्स उसकी रैंकिंग अपनी कैपेबिलिटीज हैं, वो आप लंबा भी कर सकते, थोड़ा भी कर सकते। थ्रेशोल्ड जैसे मैंने 0.8 कहा था, आप कम भी कर सकते, ज़्यादा भी कर सकते हैं। ठीक है, तो व्हाट यू विल डू इज you will find the recall for each system. So let's say मैं for query 1 की बात करूं, query 1 की बात करूं, तो let's say मैंने जब आपने recall point 1 करना है, तो how many doc I will like to, so let's say point 1 का मतलब ये है कि एक, तो recall of 0.1 basically means that one doc out of, sorry, two docs out of 20 were found। ठीक है, सो यू लुक एट योर रिट्रीव सेट और देखें कहाँ तक टू मिला था आपको। लेट्स से आपको टू फिफ्थ रैंक पे मिला है, तो आप वहां से रिकॉल निकाल सकते हैं, सो प्रिसीजन निकाल सकते हैं। तो प्रिसीजन उसका क्या होगा, 2/5 होगा। रिकॉल क्या होगा, 2/20 होगा। सो रिकॉल हमारे पास 2/20, वो 0.1, एंड प्रिसीजन आपके पास होगा 2/5 ये। इसी तरह पॉइंट 2 के लिए आपने निकालना है, आपने देखना है कि चार रिट्रीव डॉक्यूमेंट्स कहाँ तक निकले हैं। सो रिकॉल लेट्स से 4/20, 0.2 हो गया। इसका प्रिसीजन क्या होगा, लेट्स से ये चार आपके पास 9 में मिल जाते हैं, तो 4/9 ये प्रिसीजन आ जाएगा। तो ये क्वेरी 1 के लिए आप कर रहे हैं। ठीक है, दिस इज क्वेरी 1। सो सिमिलरली फॉर क्वेरी 2, ठीक है, सो Q2 पे आपके पास 50 थे, तो इसके लिए आपने लेट्स से रिकॉल ऑफ 0.1 करना है, तो आपने 5/50 करेंगे। ठीक है, अब आपने प्रिसीजन इसकी देखनी है कि 5 कहाँ तक आते हैं। लेट्स से इस सिस्टम में, अगेन ये एग्जांपल ले रहा हूँ मैं, 5 लेट्स से आपके पास 6 में आ जाते हैं, तो ये इसकी आपकी प्रिसीजन आ जाएगी। ठीक है, तो सेकंड क्वेरी की, तो इसी तरह आपके पास हर रिकॉल आपके पास ऑलमोस्ट सिमिलर आ जाएंगे, लिटिल बिट ऊपर नीचे हो जाएगा, बट यू कैन टेक द मैक्सिमम। सो अब जो प्रिसीजंस हैं वो आप फिर एवरेज कर लेंगे फॉर ऑल द क्वेरीज, एंड देन यू प्लॉट वन प्लॉट। रिकॉल सारों की वही होगी, 0.1, 0.1, 0.1, 0.1। प्रिसीजन सारी क्वेरीज की आप एवरेज करके प्लॉट कर देंगे। ठीक है, so do you get this point? So this would be the case when you are doing multiple queries, and usually we'll be evaluating over multiple queries. So for each recall, take the mean of all queries precision, ठीक है, एंड प्लॉट इट। तो इस तरह आपके पास कर्व आ जाएगा। अब इसमें एक थोड़ा सा वो हो सकता है, सो मे बी रिट्रीव डॉक्यूमेंट्स एक पर्टिकुलर क्वेरी की, लेट्स से 33 थी, ठीक है, तो इसमें आपने लेट्स से निकालना है 0.1, रिकॉल 0.1 करना है, तो यू कैन नॉट हैव 3.3 डॉक्यूमेंट्स, राइट? तो रिकॉल 0.1 करना है तो 3.3 डॉक्यूमेंट्स तो नहीं हो सकते, तो यू विल हैव 4/33. सो इट इज नॉट एग्जैक्टली 0.1. तो उस केस में वी विल जस्ट टेक द नियरेस्ट वैल्यू और उसका प्रिसीजन निकालेंगे, एग्जैक्ट हम निकाल नहीं सकते बिकॉज ऑफ द एरर ऑफ इंटीजर्स, मतलब एक से दूसरी तरफ जा रहे हैं हम, यू कैन नॉट हैव 3.3. ठीक है, तो इसी पे आप प्रिसीजन निकाल के आप एवरेज ले लें. So this is only going to be the small error that you will get. But you have to average all the precisions for the approximately the same recall and then plot it. So if you have multiple systems, एक का कर्व दूसरे से ऊपर है, in general that means that that system is better. कोई भी कर्व ऊपर होगा इसका मतलब फॉर ए गिवन प्रिसीजन उसकी रिकॉल बेहतर है, या फॉर ए गिवन रिकॉल उसकी प्रिसीजन बेहतर है. ठीक है, सो हायर कर्व्स वुड बी बेटर. ठीक है. So that's one way of doing it, using precision and recall, and using precision and recall curves for one query as well as for multiple queries. So इसमें और भी मेजर्स हैं, एंड यूजली प्रैक्टिस में आपको तकरीबन सारे मेजर्स ही यूज करने पड़ते हैं. So another measure is basically the ranked precision, or this is sometimes also called the or precision at rank k. ठीक है. So what does this mean? For a given query q, ठीक है, and let's say k is equal to let's say 10. यूजली हमारे वेब पेजेस पे हम टॉप 10, हमारा यूजुअल एक क्राइटेरिया होता है कि टॉप 10 में फर्स्ट पेज ऑफ योर वेब रिजल्ट्स पे क्या रिजल्ट आ रहा है. ठीक है, सो इफ k इज 10, सो हम देखते हैं कि इस टॉप 10 में हाउ मेनी ऑफ द डॉक्यूमेंट्स आर रेलेवेंट. ठीक है, सो so so that would be your precision at k. So precision of a particular query given k, in this case is equal to 10, let's say. So this is basically, uh, let me write in words, number of relevant docs in top 10 divided by 10. ठीक है. So अब यहाँ रैंकिंग को एक्सप्लिसिटली यूज कर रहे हैं. इन द प्रीवियस केस रैंकिंग को हम एक्सप्लिसिटली यूज नहीं कर रहे थे, एंड दिस इज इम्पॉर्टेंट, more important, especially when you have applications like web search and library retrieval and so on. Ranking is important because कोई भी दूसरे पेज या तीसरे पेज पे नहीं जाता, पहले 10 पेज पे या पहले 5 रिजल्ट्स को देखता है. ठीक है. सो दिस इज कॉल्ड प्रिसीजन एट रैंक के, और के आप यूजुअली मल्टीपल यूज करते हैं, मे बी k3 होगा, k5 होगा, k10 होगा. 10 से ज़्यादा जनरली कम होता है फॉर मोस्ट एप्लीकेशंस. ठीक है. So we find how many documents were found in the top K. Let's say K5 है तो 5 में देखते हैं कि क्या था. एक मिला डॉक्यूमेंट तो 1/5 प्रिसीजन होगा, दो मिले तो 2/5 होगा, पांच पूरे मिल गए, सारे पांच रेलेवेंट थे तो 5/5 1 होगा. ठीक है. एंड ऑफ कोर्स इफ यू हैव मल्टीपल क्वेरीज, so simply take the mean average. So this is basically called mean ranked precision, MRP. ठीक है. So if I want to write this 1 divided by q So this is a summation operator, q in q, ठीक है, and then you have of course the precision here. So precision at for query q k, ठीक है, एवरेज ले सकते हैं. So this is called the mean rank precision or the mean of precision at rank k for multiple queries. By the way, in this case as well as in the previous case, higher values are better. ठीक है, precision recall higher values better, rank precision higher values are better. So just one more before we start. Actually, there are two more. One is the other major is called the reciprocal rank. ठीक है. So this is another measure, sometimes called RR. इसका भी मीन निकाल सकते हैं, मीन RR हो जाएगा. ठीक है. So what is this? Basically, this looks at the first relevant document. The first relevant document of a query. Sorry. ठीक है. So let's say आपने एक क्वेरी की क्यू और आपको जो फर्स्ट रेलेवेंट डॉक्यूमेंट पोजीशन 1 पे मिल गया, तो इसका रेसिप्रोकल रैंक वुड बी 1 और 1. ठीक है. सो इफ फर्स्ट डॉक फाउंड फाउंड एट रैंक लेट्स से 5, तो इसका आरआर क्या होगा? 1 और 5.2. तो इसमें पहले 4 डॉक्यूमेंट्स इररेलेवेंट थे, पांचवा रेलेवेंट निकला. फर्स्ट रेलेवेंट जो था वो पांचवा था, तो इसका आरआर 0.2 होगा. इफ फर्स्ट रेलेवेंट डॉक्यूमेंट ही रेलेवेंट था तो 1 और 1, इसका 1 होगा. एंड इफ यू हैव मल्टीपल क्वेरीज, आपने उसका एवरेज ले लेना है, मीन आरआर आ जाएगा आपके पास. और फाइनली फिर आपके पास है मीन एवरेज प्रिसीजन. ये मैं वैसे नेक्स्ट टाइम डिस्कस करूंगा, इसी तरह का ही है ये भी, बट जस्ट टू मेक श्योर कि ये आप ओवरलोड नहीं हो जाएं, तो नेक्स्ट क्लास में थोड़ा सा प्रीवियस का समरी के साथ इसको मैं कवर कर लूंगा. मीन एवरेज प्रिसीजन. ठीक है. सो व्हाट वी हैव कवर्ड सो फार. सो सिंपल प्रिसीजन रिकॉल, और इसका कर्व भी इंपॉर्टेंट है. ठीक है. एंड देन वी टॉक्ड अबाउट ranked precision, and of course mean rank precision, and then reciprocal rank and mean reciprocal rank, and then finally MAP next time हम discuss करेंगे. So usually all of these would be done for any evaluation of a system. एक से काम नहीं चलेगा, because each of them gives you a different perspective. For example, ranked precision gives you के टॉप 5 में क्या इसकी परफॉर्मेंस आ रही है, टॉप 3 में क्या आ रही है, टॉप 10 में क्या आ रही है. ठीक है. एंड ऑफन टाइम्स इवन इन एडिशन टू दिस ह्यूमन इवेल्युएशन भी हमको करनी पड़ती है. ठीक है. ऑलराइट. सो आप लोगों की जो रीडिंग है, बेसिकली रीड अबाउट द हिस्ट्री ऑफ गूगल, गूगल सर्च, अल्टा विस्टा पढ़ें. ठीक है. अच्छा, आपने क्या स्पेलिंग मैंने गलत लिखा हुआ है, आपने क्या बताया मुझे? ठीक है. एंड ऑफ कोर्स read chapter 11, section 11.1. So in the next class, we'll wrap this up and then we'll start about logistic regression, okay, which is a classification technique. So any अच्छा, तो ज़्यादा तो इसमें ये मेजर्स ही थे एंड पे. तो मेजर्स आपको मिल जाएंगे बुक में 11.1 के सेक्शन में मिल जाएंगे. बाकी कहानी जो पहले थी वो तो लास्ट टाइम की continuation थी tf-idf. We covered it in the last lecture as well. Anything else? End of next week. इस वीक ये वीकेंड तो है आपके पास जो अभी आ रहा है, तो एग्जैक्ट डेडलाइन मुझे वैसे नहीं पता. सो आई विल चेक ऑन दैट. यस. हमने रैंक पेज की बात कर रहे हैं. रैंक पेज का हमने कंसिडर नहीं किया. वी सिंपली लुक्ड एट द क्वेरी इन टर्म्स ऑफ टोकन्स एंड और वर्ड्स एंड द डॉक्यूमेंट. रैंकिंग हम खुद ही कर सकते हैं और की है हमने कोसाइन सिमिलैरिटी से या स्कोरिंग से. जिसका स्कोर ज़्यादा होगा वो ऊपर आएगा, जिसका स्कोर कम है वो नीचे आएगा. So, so the scoring function is important. So that's used for ranking. अच्छा, ठीक है. सो आई डिडंट क्वाइट अंडरस्टैंड कीवर्ड का दूसरा लफ्ज आपने क्या यूज किया. बिडिंग का मतलब क्या हुआ. सो वी आर एक्चुअली यूजिंग एग्जैक्ट मैचेस ऑफ कीवर्ड्स. और सेमेंटिक मैचिंग नहीं हो रही, वो हम आगे जाकर डिस्कस करेंगे when we talked about dense representations of words. So here we are actually looking at if a word occurs in the vocabulary, then it will match, otherwise it will not match. ठीक है. So anything else?